if anyone did her undergrad at Cambridge, and she's finishing up her PhD at CITA, her advisor is Planetary. She's worked on a bunch of things like Kuiper belts and the formation of the testaments. She's talked about some of these things.
Thank you very much. It's a great pleasure being here, and so I'd like to take this opportunity to share some of my research with you, and even some of the work I've been doing last week. So I have quite an ambitious plan here. So I divided up the talk in 3 parts. I'd like to start with talking about the accretion of planetesimals and the effect it had on the planetary spins, and introduce a new model we have for this. Then, in the second part, I want to spend talking about the formation of capital binaries and observational signatures, different formation scenarios lead that we can test today. And then some brand new stuff, which I'm working on right now, and it's related to measuring the size distribution of small capital objects by stellar occultations and using the fine value census of HST. So, planetesimal accretion. So for this part, there are 2 or 3 terms I'd like to define to make sure that everybody knows what I'm referring to. So the prograde, I mean, a planet that's spinning around its own spin axis in the same sense as it goes around the sun. And with retrograde, I'm referring to a planet or a protoplanet that spins in the opposite direction to the object in which goes around the sun. And then the obliquity is just the angle between the spin axis to the normal of the orbit. So if you look at the spin axis and the sense of rotation of the planets in our solar system, there's probably 2 things that will strike your eye. First of all is that their spin axes are pretty close to being perpendicular. All of them have angles of less than 30 degrees, apart from Uranus. And then most of them rotate in the same direction in which sense is prograde, with the big exception of Venus. And even without doing any detailed calculations, you can see that this is a configuration that is not random. However, the standard formation models, at least with terrestrial planets, would predict that the obliquities and spin directions, at least for the terrestrial planets, should be random. So how does a planet gain its spin angular momentum? So there are 3 stages in which a growing planet, at least a growing terrestrial planet, acquires mass and therefore angular momentum. In the first stage, you grow planetary embryos by the accretion of planetesimals. Once what we call an isolation mass is reached, so once roughly the mass of the planetesimals is comparable to that that's already existing in protoplanets, becomes comparable, the planetesimals are no longer able to dam the random motions of the protoplanets. The system dynamically excites itself, and you get giant impacts.
Can I, sorry to interrupt with a technical...
yes.
Can you check that the mic is on?
It's not blinking.
Is it green?
Huh?
Is it green?
No.
Let's check. So we'll just hold down the button.
Maybe I'll just continue and then... Okay. And so the system gets dynamically excited, which leads to giant impacts, which in the inner solar system tends to, you'll have impacts, whereas in the outer solar system, you'll tend to have ejection of bodies because the escape velocity from the sun is lower. So then you have a phase of giant impacts, and our moon is thought to form from one of those. And then the last stage in accretion for terrestrial planets is the cleanup of the leftover planetesimals. This stage is necessary because, well, not only because these giant impacts will have set elements on some material walls and small bodies, but also because small bodies are needed to damp down the eccentricities and inclinations of the terrestrial planets to get this low inclination and low eccentricity configuration we have today. And this will give our final planet with a spin. So I'm going to go through all these 3 stages and discuss So we can place our moon up to about 200 times the radius of the Earth, but not further. If it would be placed further, it would have to orbit around the Sun instead of being a moon of orbit. And our moon is actually quite far out. It's a quarter of this maximum distance it could be. So in this diagram, it's drawn in the so-called rotating frame. So the Sun, you must imagine, being down here. And so it's fixed on this protoplanet. So the whole system is rotating like this around the Sun. So the x-axis, if you want, is always pointing radially outward, and the y-axis in the prograde direction. So in standard planetesimal equation, these protoplanets grow by the direct collision of planetesimals from the disk. And this is what I've drawn here in these blue bands. So you can calculate analytically where these particles have to originate such that they directly collide with the protoplanet. And already from this drawing you can see, or from this actual part of the planetesimals, you can see that you expect to get very little angular momentum, because all planetesimals that originate in this part of the accretion band will tend to spin the planet this way, and those originating from this part will tend to spin the planet in the other way. And if you do a detailed calculation, you can show that if a protoplanet accretes from a dynamically cold planetesimal disk, you expect that it has essentially no rotation. It has very, very little retrograde rotation, but it's so little that it's essentially never important. We have shown that if planetesimals are sufficiently small, then they're more likely to collide with one another inside this Hill sphere of the protoplanet than to directly collide onto the protoplanet. So in this idea is that, so planetesimals collide, they'll come, due to their collision, one or both of them come bound to the protoplanet, and they form a disk of planetesimals around it. And so the protoplanets will grow by accreting this planetesimal disk instead of having these direct collisions. And so you can calculate when this regime will apply. So if you compare the collision rate of two planetesimals within the Hill sphere of the protoplanet to that of direct collisions, you find that the semi-collision accretion will dominate as long as the planetesimals are less than around 10 meters in size. So if planets are sufficiently small, this would be the dominant way of growing. And there's pretty good reason to believe the planetesimal is small, because even if your first planetesimal start off as a kilometer, say, these planetesimals will be dynamically excited due to scatterings of large bodies, and so it will be an onset of a collisional cascade that will break the planetesimals into smaller and smaller particles, and the lower limit of the planetesimals given would either be, the lowest it can be will be basically at which velocity the disk becomes locally dynamically unstable to gravitational collapse, so you can form again a larger planetesimal, or if you have enough gas present, it might not go down all the way to that small size, but it will stop somewhere before. So there's good reason to believe that planetesimals really are that small, in which case the picture of planetesimal accretion is very different from what's usually thought.
What's the difference in semi-collisional and collisional?
Oh, yes, the collisional it's here. Sorry, I didn't discuss it. Semi-collisional just means that planetesimals are more likely to collide with one another than to directly collide onto the protoplanet. Collisional means that they always will collide when they cross the Hill sphere. So this is kind of like a fluid, a complete fluid. And so we looked at the angular momentum that is carried by these planetesimals into the Hill sphere, or a distance of the effective accretion radius. So this is scaled. So this is the Hill sphere. So one would be the Hill sphere. This is a specific angular momentum by the planetesimals. So if we have direct accretion, the only planetesimals that will hit the planet and the planet will grow by are those that directly collide with it. And so we're in the regime down here. So the radius of the planet to that of the disk sphere is very small. So we're all the way down here, and you can see you get very little slight retrograde angular momentum. And that's That's the non-result I discussed before. If I already have a semi-collision or collisional accretion, now the effective accretion radius of the planet is much larger. It's more comparable to the Hill sphere itself, and you can see that the planetesimal disk that forms has large prograde angular momentum. So protoplanets that grow from accreting such a planetesimal disk will be rapidly spinning in the prograde sense.
So if you thought of it as just an ideal gas disk in which you accrete, then wouldn't you expect it to be retrograde just because the particles interior to your orbits have a higher angular velocity than you do? So if I go on.
No, so naively you expect it to be prograde. So if you look at this drawing, and we say now all the material that comes in here and all the material that comes from here, right? This material, if you move in that direction, this material.
Where's the sun in this picture?
Down here. So again, in this rotating frame, that this is greatly pointing outwards.
Yes.
So we have material approaching these two waves, right? And so you're right. In this picture, the angular momentum you would get is in this direction.
That's not the way.
Yeah. And this is exactly minus 3/4 omega r squared. So this is this square. But what you forgot is that the frame itself also has an angular momentum, because in this frame I fixed that the x-axis is always pointing upwards. So this part, if they want to bring it back in the inertial frame, this frame itself has an angular momentum of omega. And so if you add them together, it's plus 1/4. So the net angular momentum you expect from a gaseous disk is prograde. And that's exactly that limit you get if you move up. So the combined part is plus 1/4 RH squared. So it's just because you're looking at this fixed frame, because in this frame your coordinate system rotates like this, so you need to count this on. Okay, so if you now form these protoplanets.
So just to follow, so sorry to interrupt you. So this depends on the ratio of the epicyclic frequency to that of your orbital frequency. So if you change, I guess not relevant to our solar system, but if you change the potential galactic, for example, you could get a different potential rotation. You're saying that the epicyclic frequency is faster than the orbital frequency, which causes you to give this cancellation.
No, so this here is not even considering any epicycles at all. This here is just from the shear, from the capillarity shear. This velocity here is just what you expect because you're further away. So basically, it's just a differential shear. It's not even. So this for circular orbits, no epicyclic frequency.
So it does change if you don't have a capillary wall.
That's right, and also it changes if you have a. So it would, but here, even in this very first picture, you don't even have epicycles. Or if you can, the zeroth order case would just be a cold disk, so not even epicycles. Yeah, this was keeping in mind with our own solar system, not okay, so if protoplanets form from small planetesimals, you would have a system of rapidly spinning protoplanets with maximal rotation. So the next phase would be these giant impacts. And so just considering a very simple model, by having we start off with all bodies having the same mass, little m, and then we have accretion one by one, so that after n accretion events, the total mass of our planet will be n plus 1 times the original mass. If you have a toy model of what the angular momentum should be. So if we just look at the angular momentum from giant impacts, now first, assuming there's no spin, we get that the RMS angular momentum in the z direction is given by this 1/7 square root the number of impacts, so the minus 1/2. Omega crit is the critical spin-up velocity, or the critical breakup frequency. M is the final mass, and R is the radius squared. And so for 20 then impact, that's roughly the number we'd expect for our Earth. You get a spin period of 4 hours. And you'd expect the obliquities to be random and equal likelihood for prograde retrograde rotation. And in body simulations find something close to that. Actually, the spin period is somewhat shorter because of somewhat unphysical collisions. There's always assumed that a collision will result in a merger, even if the impact velocity is much higher than the escape velocity. But now, if these impacting protoplanets also have a spin, you get not only this random spin component, but you also get a systematic spin component because they were all maximally spinning in the same direction. And again, so using the same impacts, we can now calculate the systematic spin component, which I call here as the spin, and it's given by a 2/5 and a minus 2/3. Again, the omega, the critical breakup frequency, and M and R squared is the same as before. So now there are two competing facts. You still have the down impact, and they're still random, and they give you some random component. But the final spin of the planets also has a systematic component. So if you would look at the spin distribution, or the distribution of the angular momentum, you have a mean that's given by the prograde part, and then you have a standard deviation given by the random part from just the random direction of the down impact. And so for 20 or so down impacts, you'd expect around 70% of all terrestrial planets to be prograde and 30% to have retrograde spins. So there is a signature left and a preference for prograde rotation.
So you got kind of 2 hours. I thought the Earth's breakup speed is 90 minutes, isn't it? The orbital speed is 90.
Yes.
Which is a breakup speed.
Yes.
But that's almost a breakup speed. But that's equal to omega crit mr squared.
You mean the 2 hours?
Yes, in 2 hours.
No, I'm not getting the 2 hours. The 2 hours comes from people who do n-body simulations who exactly don't account for the breakup speed. They just always merge. Any encounter, they always say if two bodies collide, they'll merge into a bigger body, which is not correct. That's why they get an unphysically low 2 hours. That's right. And then the final stage of accretion would be this final cleanup after the giant impacts. So as I said before, we expect there to be significant amounts of material left because giant impacts set in when there's still a lot of mass left in smaller bodies. Once their surface density is comparable to that of the mass surface density of the large bodies, you produce new planetesimals because in the collisions, even if they're mainly accretional, you still break up and create new smaller particles. And you can also show that around 7% of the total mass of the system still needs to reside in small bodies in order to be able to damp the eccentricities of the terrestrial planets. And if only 10% of the Earth or 3% of the mass would have been accreted in the semi-collisional manner after the giant impacts, it would be sufficient to supply the entire angular momentum of the Earth-Moon system and Mars respectively. But then I'm not saying that the Earth-Moon system and Mars got the entire momentum from the post-giant impact accretion, but even if they could just a really small fraction of their final mass in that last cleanup stage, they will have significantly altered their spin properties, and again, it would favor prograde rotation and low obliquities. So to summarize, so the growth of planets might be dominated by the semi-collisional accretion, and it leaves a signature in preference for prograde rotation and obliquities that are smaller than you'd expect from random collisions. And obviously would like to compare it with what we know from our own solar system. Unfortunately, this is a little more difficult than I thought when I started off with this project. So Venus is probably not a good data point to compare with because the spin of Venus has evolved considerably due to atmospheric tides, coronal friction, and probably even some chaotic evolution. And therefore, so basically people even argue whether it started off prograde or retrograde. So we don't know for sure. Mercury is locked in a 3-2 spin orbit resonance with the Sun. But nevertheless, we can be pretty confident it should have started out prograde to be captured in its current state. So although its spin axis probably is not very significant for testing this model, at least its center of rotation should have been prograde. And the spin properties of Earth and Mars have evolved much less, and they're both consistent with being prograde and having pretty low obliquities.
Sorry, you meant if Mercury started being retrograde, it would not be able to turn into current state?
Yeah, I think it probably should have stayed at the 1-to-1.
Retrograde?
Yeah, oh, yeah, just with the, it's a synchronous state before, because it would have to go synchronous and then evolve back out, right, to turn it prograde. I can't see how you could start retrograde and then evolve in the prograde 3D2. Just another resonance.
It's the opposite. Could you start prograde and evolve into retrograde?
Can you? You asking me? Yeah, I mean, people think Venus has done that, but because of its atmospheric tides. Most people believe, from reading the literature, most people believe that Venus started off prograde, and I mean now it's slightly retrograde, but if you compare its rotation around its own axis to the orbit around the sun, it's nearly the same. It's very close to.
You sure? Do we know that if Mercury starts being retrograde, it will not be tilted back to this Cassini state?
Yeah, that's
Because Cassini state is stable, right? So
yes.
it's stable with
Yes.
any other state.
Yes. Yeah, that's why I think it would.
The argument is that by continuity, it would have to, on the way from retrograde to the current state, it would have passed through the 1-to-1 resonance.
Right.
And people just think we just stuck there.
Right.
I don't know. I don't know the answer.
You also give a relation between obliquity and spin?
So say again?
Can you give a relation between obliquity and spin?
Spin theory?
Yeah.
From
For different types of accretion, you give different relations between obliquity and spin, or they all give you 0?
For this model?
Yeah. Obliquity.
Yeah, I think there should be a relation. At least statistically speaking, there should be a relation. Yeah, but it's not really testable for.
For Mars, you can test that?
Say again?
For Mars, you can test it.
Oh, you mean throughout the evolution, or you mean just?
Today. You can say what.
Sorry, I think I didn't understand. You're asking.
Well, we know Mars is obliquity and its rotation rate.
Right.
Does this theory predict something for that?
So it depends on the number of jet impacts you must have had. So that's like a bit of an unknown.
So there's an extra frequency.
Yeah, that's right.
Okay.
So basically, I mean, what we can. So if you would have a large statistical ensemble of planets, terrestrial planets or spins, you could definitely do a very quantitative comparison. Comparing it with the so far other generally accepted standard model of formation of terrestrial planets, I would say it does much better because they expect obliquities that they're with equal likelihood between 0 and 180 for all of the terrestrial planets, because that's what you expect from giant impacts. There's nothing, if they're truly random, there should be no preference for small obliquities of any kind. And even getting even 2 planets with obliquities less than 30 degrees can be ruled out by, it's quite unlikely if there's this. I mean, ideally you want to test it with a larger sample of terrestrial planets, and maybe one day we'll have extrasolar terrestrial planets, but even then getting their spin will be another step from there. So maybe within my lifetime we might be able to test it, but it's nothing within the next 10 years. You can also look though at the asteroid belt. So planet formation in the asteroid belt was kind of interrupted once neighboring planets were massive enough such that they stirred the velocity in the asteroid belt, such that mutual encounters between particles started fragmentation rather than accretion. However, like evidence from the vast of asteroid belt suggests that the very largest objects in the asteroid belt might have actually kept their original spin, or their spin properties have only evolved very little. And if you look at the two largest objects in the asteroid belt, Sirius and Vesta, you will find that they too both have pro-rate rotation. And even if you look at slightly smaller main belt asteroids around 100 kilometers inside, they also still, as an ensemble, show a preference for pro-rate rotation, which has not really been explained in any other way. So that's all the comparison I think we can make with our own solar system. So I think I'll move on to the binaries from here, if there are no more questions. Okay, formation of capable binaries. So I'm sure you all know the Kuiper belt is a disk of icy bodies located beyond the orbit of Neptune at around 40 AU. More than 1,000 objects have been discovered to date. And I guess one of the first surprises was that a large fraction of these objects are binaries. So it's really a perfect place for binaries. Today, about 50 binary systems are known, and more than a dozen of those systems have well-determined orbits. The overall binary fraction is around 10%. It's actually much higher in the coexacial Kuiper belt than in other dynamical classes like the scattered or resonant population. Broadly speaking, we can classify these binaries into two classes. Those with a high mass ratio, so 10 to the minus 4 to 10 to the minus 2, their formation is probably similar to what we think how our moon has formed. So you have an impact, and then you have some time evolution outward, which would then form your system. The second class consists of comparable mass ratio binaries, and they have been very interesting because they are equal mass and very far apart, like a large fraction of the hill radius, which is like this maximum distance that could possibly be. And because of this large angular momentum the system has today, their formation must have had a dynamical origin, because an impact scenario with tidal evolution outward would not work because the system would have too much angular momentum. So if you look at the angular momentum it has now and try to evolve it backward in time, it would be spinning much faster than breakout if you try to have these bodies in one place. And so many groups proposed formation scenarios to explain those wide binaries. One explanation still involves a collision. So you have a collision in tidal evolution. That's kind of the same as for the high mass ratio case. And then you have an exchange reaction that swaps the smaller moon with one of an equal mass body. The bottleneck in this part is probably the timescale for the tidal evolution outward. So it needs to be sufficiently far away that an exchange reaction becomes likely. Then there has been a formation scenario proposed by Weidenschilling. Basically, in this scenario, you have two capable objects collide within the Hill sphere of a third. Due to the collision, one of the objects becomes bound, and you get a binary. However, instead of needing a collision, it's sufficient to have three bodies gravitation deflect. So again, you have two bodies that come within the Hill sphere of a third, but now you just have, it's sufficient to have a gravitation deflection to get rid of some energy, and you can form a bound binary. And this mechanism will dominate over this collision because the cross-section is just much larger. And this is proposed by Goldreich et al., and one of the authors is sitting in the audience. And then you can also form binaries by having a transient binary with two capable objects, but then you have dynamic friction that's generated by a background population of the small particles from which the bodies still grow that dissipates the energy to form a bound system. So I will focus on these last two in the remainder of my talk. So there are two different regimes one can consider. In the first case, what we call subhill velocities. That means that the disk is essentially 2D. So the velocity dispersion is so low that the bodies actually pass above one another. So it's really like a two-dimensional disk of parabolic plates. And then the superhill velocities, it's a 3D disk. So the hill velocity is, again, it's the velocity you'd have two objects that orbit each other in separation of the hill radius. So superhill velocities is like a 3D problem, and the subhill is more like a 2D. And we have shown that if you compare the formation rate for having a three-body encounter to that of forming binaries with dynamic friction, that forming binaries by dynamic friction will always dominate over that by three-body encounters in the subhill velocity regime. So the formation rate for forming binaries by three-body encounters is basically given by the rate of having three bodies within the Hill sphere together. The formation rate of the forming binaries by dynamic friction is given by having two bodies in the Hill sphere together times this dP is this coefficient of dynamic friction, which parameterizes how much energy is lost in the orbital time scale. And you can show that this d can be replaced because the velocity dispersion of the large bodies is damped by the dynamic friction experienced on the small bodies. You can replace this, and you can show that all it depends on is the velocity dispersion of the large bodies times a small number. So as long as the velocity dispersion of the large bodies is less than the hill velocity, dynamic friction, forming binaries by dynamic friction will be the more efficient way. For superhill velocities, this picture is reversed. Now, essentially, dynamic friction is not able to dissipate enough energy in this given encounter. So the forming binaries by having a three-body encounter is the only way that it could proceed. If you look at the stability of prograde and retrograde binary orbits, you find that two bodies that orbit each other in the retrograde sense, so in the opposite sense in which they go around the sun, and you can place them at much larger separations and they can still be a stable bound binary than if they would be in a prograde orbit around each other. And this is due to the Coriolis force. The Coriolis force for a retrograde binary acts inwards, so it tends to stabilize the system, whereas for the prograde binary it acts outwards, so it tends to destabilize the system. And this is actually a well-known phenomenon in nature. If you look at the irregular satellites, they're on retrograde. And it's exactly because they're taking advantage of this extra stability in the very outer parts of the Hill sphere that only exists for retrograde orbits. So if I take our Earth moon, I can place them much further from the Earth on a retrograde orbit than I could put them if the moon would be on a prograde orbit. And this actually has very interesting implications for the two different binary information scenarios I'm discussing. So basically I just ran a simulation and formed binaries by letting three bodies encounter each other, and then looked what kind of systems do you get, and it wasn't a surprise. You'll find that the widest binary, so basically this corresponds to very wide binaries, close to the outer parts of the Hill sphere, and it's a very tight system. This actually is in the units of the Jacobi constant in Hill units, but if you're not familiar with it, it's not so important. Basically, it's just a measure of the separation. So very wide system and very tight system. And you find these are the retrograde binaries and these are the prograde binaries. And as expected, you find that in the outer part of the Hill sphere, you get only retrograde systems. There are no prograde systems in this region. Once you're sufficiently narrow, once the orbit is sufficiently tight, this difference goes away and you can have prograde and retrograde binaries. So now, if you look, forming binaries for these three-body encounters, if you look at the binary fraction of the fraction of prograde to retrograde binaries, you find that around 2/3 will be retrograde and only 1/3 prograde if you form the binaries from a cold disk, dynamically cold disk. If you form binaries from superhill then the chance of having a prograde versus a retrograde binary is 50-50. Because now, once the velocity spread is large, you could still form wide binaries, but they'll be broken up again by passing bodies. And so only the tightest systems will be safe from breakup. But for the tightest systems, it doesn't matter anymore that in the outer part of the Hill sphere, retrograde orbits are more stable. And so this preference goes away. If you now look at the binaries that form with the help of dynamic diffraction, the picture is very different. Because if you want to form a binary with dynamic diffraction, the first, the initial binary you form is kind of the widest binary possible, right? Because dynamic diffraction only dissipates a really small amount of energy at any given time. So the first binary you form will be very wide, and because the widest orbits in the Hill sphere are only stable for retrograde binaries, all these binaries will start off retrograde. With time, their orbit will shrink due to dynamic diffraction, but the sense of their rotation will remain the same because there's nothing to switch it around. So binaries forming by dynamic diffraction should all be retrograde. There might be a small fraction that can be prograde because you might have some exchange reactions, but you can show that it should be less than 10%, and we actually did also some detailed simulation that show this is like 3%, and that are broken up or exchanged. So really the vast majority of all binaries that form this way should be retrograde. So to summarize, if binaries formed in this when subtle velocities prevail in the Kuiper belt, they should have primarily formed with the help of dynamic diffraction, and their orbit should be retrograde. If they form while superhill velocities prevail in the Kuiper belt, then there should be equal chance of prograde and retrograde binaries. The nice thing is that this is actually something that we'll be able to test with observations within the next few years. They have, we don't really have a good sample for which we can test it yet, because although we have around a dozen or so binary systems with well-determined orbits, the solutions we have are degenerate with respect to the prograde and retrograde solution. And the reason for this is that it's difficult to distinguish an orbit, say, that goes in that sense, this way, or an orbit that goes in this way, because you cannot see which body is in front if you just see the projection into the sky. And one of those two is the prograde solution, and one is the retrograde solution. And this is why, although we have a dozen or so well-determined orbits, the solution is degenerate in the prograde and the retrograde case, or nearly degenerate. So what you actually have to do is you have to wait in time until the opening angle of the orbit changes. With time, our perspective of looking at the binary will differ because of the relative motion between us and the binary around the sun. So we're viewing the system at a different angle. And only after a few years, observing the same system again, we'll be able to break this degeneracy between the prograde and the retrograde solution.
The few years is the timescale of the orbit of that binary?
No, the timescale of the orbit of the binary is between like 20 to 200 years. But in a few years, has the viewing angle between an observer on Earth to the binary changed enough that by getting additional observations, you can usually exclude one of the orbital fits because they're not good anymore. So the orbit kind of starts to opening up or to close on you. Yeah. You're lucky you don't have to wait like 200 years. That will be easier. Nevertheless, so last year, or like a few months ago, there have been two unique solutions reported. One for a scatter disk object, which is found to be prograde, and one for a cold classical Kuiper object that's found to be retrograde. It's kind of too early to draw any conclusions from this, but it kind of tentatively suggests that maybe binaries form for a slightly dispersion-dominated Kuiper disk. The main future question, I think, in my opinion, to address in the binaries is really their evolution after the formation, and if they're, what were the effects of the dynamical excitation of the Kuiper belt and the binaries, and dynamic friction. And they also there might have been some resonant evolution. So that's future work. And then in the very last 10 minutes, I want to share some exciting new work with you. So I'm leading a project that aims to measure the size distribution of small capable objects. And small now means objects that cannot be directly detected from Earth. Objects that are so small in the capable they don't reflect enough sunlight that they can directly see them. And I'm not doing this work on my own. My collaborators are Aaron Offwick, Ran Sari, Aushai Gayam, Ed Neil, Mike Wen, Shai Zucker, and Mark Media. So why do we care? The size distribution gives us interesting information. The slope of the size distribution will tell us about the formation process, the accretion process in the capable. The location of the break radius will tell us about the collisional history. Basically, for how long have these collisions been going on, breaking up bodies. Because with time, the size at which bodies can be broken will move to larger and larger sizes. So we wait another few gigayears, it'll move to, right now it's around, say, 20 kilometers. If we wait another few gigayears, it'll move maybe to 100 kilometers. So it tells us for how long destructive collisions have been going on in the capitol, for how long the velocity dispersion has been excited in the capitol. And then the power law index below the break tells you about the material properties. You expect a different power law index, whether these bodies are dominated by material strength or they just rubble piles. And so this size distribution is usually parameterized by the NPRs, the number of objects per radius, and it's proportional to the size, and this power law index is Q, so it's minus Q. And so basically, from observations directly detect different objects in this regime. So roughly down to, say, 10 or 20 kilometers in radius. And so to learn anything about, maybe the break might be weakly constrained by observations right now, but to learn anything about the slope below the break, you'd need to detect capable objects indirectly. Or here, that's what I said. So if the power law index for small bodies would be 4 or larger, the conclusion would be that there was no collision evolution in the capable, and this continues from large bodies down to small bodies. If the power law index would be around 3.5, this would be, the conclusion would be there was collisional evolution. This 3.5, most of you probably know it. It's famous Binaries spectrum, and it would imply that capable objects held together by material strength. An even shallower power index of 3 would hint that yes, there also was some collision evolution, but that these bodies behave like rubble piles, meaning that they lack a significant material strength and that they're held together predominantly by gravity. You must imagine just like a big pile of rubbles, and they're just held together by the gravity. So they're very easy to disperse and break. So what's the solution? So people proposed many, many years ago, you could actually detect a small capable object by stellar occultations. You don't observe them directly because you can't detect any light from them, but what you do is you monitor a large number of stars and you wait and see whether you can detect some dimming. In this way you could constrain how many objects there are and what their power law index might be for the size distribution. The problem with that is you need these occultation events obviously rare. It's a chance event that a small capable object will pass in front of a star, and they are very short duration. So two things that are key to any survey which wants to do this is you need a long timeline. So you want to look at as many stars as possible for as long as possible, and you need to sample at a very high frequency because these occultation events typically only last a fraction of a second. So you need a very, very high sampling frequency. And there have been several surveys that have tried to do this. Maybe the most promising ground-based survey is the TARAS project. They built several dedicated telescopes that monitor several stars every night, looking for such occultations. But there have been several other projects as well. There has been one space-based survey using X-ray observations, and our project also uses a space-based survey, but it's invisible. One of the advantages of doing it in the X-ray is that you can probe smaller objects, but unfortunately you're photon limited. Yeah, none of those surveys have, I would say, reported any observations that are generally believed. So what do we do? We successfully proposed to use the fine guiding sensor of HST to look for those occultations. So HST has 3 fine guiding sensors that are used essentially just for HST to guide and be locked in the right position while the main instruments take the data. However, they turn out to be perfect for our purposes because they continuously record the photometric data of stars at a 40 Hz frequency, which is like perfect. And we have 10 to 17 years worth of observations because we're going to analyze all the past observations that have been taken with the fine guiding sensors, which really were never intended for science purposes. They were only for guiding the instrument. But this is also a problem in our case because there doesn't exist an archive that's easily accessible for scientists. So part of our project actually involves creating such an archive such that this data will also be available to the rest of the astronomical community. So I said those two. This is kind of roughly what we'll be looking for. So you can see the time scale is very short. This photon counts of some actual data we have, and it's a simulated event. So you can see that because of the very high resolution and the short sampling frequency, we can actually resolve the actual diffraction pattern instead of just some dimming. And that's actually very good and very helpful because this way we can detect small objects, be more sensitive. Because this was never targeted just to do look for occultations in the Kuiper belt, a large fraction of our observations will also be observations of high ecliptic latitude stars, and we'll be using those as a control sample because this will allow us to check now for instrument effects and so on. Because we shouldn't, if we find our majority of objects or occultations and high ecliptic latitude, that means that there's probably something else we're seeing and not really occultations. And there are at least 2 fine guiding sensors acquiring data simultaneously. So we also have some means of checking against false positives because of instrument jitter or other things. So what do we expect to see? So the shape of the light curve depends on the wavelength you're using and on the object size. So we'll be looking at the visible around like 500 nanometers. And so the Fresnel scale is given by roughly 1.3 kilometers. So an object of a kilometer would result in a diffraction pattern given by this red line here. It will be right on. The impact parameter is 0. And you can see it's a very strong signal. If it's slightly offset, so if it would be offset by 2 Fresnel scales, then you can see a lower amplitude signal, and also the shape is quite different. So in the Fresnel regime, the details of the diffraction pattern changes on the geometry and even depend on the object shape. In the Fraunhofer regime, the diffraction pattern is much more generic. It does not change anymore with impact parameter. You see here, it's the same difference in impact parameter, and the blue and the red curve look pretty much the same. It doesn't depend on the shape of the object, and this makes actually our search for signal quite easy because we can use one template, and then the width of this template is just given by the relative velocity of the observations, the velocity between us and the capable object, and then the height of the template is just given by so the amplitude of the signal is just given by the radius squared of the object itself. So you can just solve or fit for the amplitude of the signal. So that's actually quite nice and gets rid of a lot of uncertainties and ambiguities. So what do? So we search, so we get the data stream, we search for events by fitting this light curve template I've shown you. There are three parameters. There's the velocity, which is the width of the template, the amplitude, which is given essentially by the object size, and the mean is just the mean number of counts. It just depends on the star we're looking at. Then if you find a significant event, then we go back and look at what kind of guide star were we looking at. Was the guide star in a reasonable position? Was it within, say, 20 or 30 degrees of the ecliptic, or was it completely off? Was the subtended angular size of the guide star less than the Fresnel scale? Because if the guide star subtends in size comparable or like the Fresnel scale, you shouldn't get any diffraction effects. Then, even more, we can compare the velocity we get from our fit to the velocity of the observations. This is probably one of the strongest constraints in ways of checking we have, because we get a velocity from the fit, just from the width of the signal. But at the same time, we know from the observations what the velocity should have been, because the velocity of the event is given by the Earth velocity, the velocity of the Kuiper belt object, and then you also have to account for HST velocity at a given time. But we know all of these; they're not unknowns. And as long as the random motions in the Kuiper velocities version is low, that it's not comparable to these 4 kilometers per second, which is true for most Kuiper belt objects, we can constrain this velocity very well. So it's a very good check, because if the velocities don't match, then this probably didn't observe a real event either. And then we can still check the event rate we have as a function of latitude. Do we find many more events for low latitudes than high latitudes? And there should also be a function on the event rates on the relative velocity.
Is there only one wavelength?
Say again?
There's only one wavelength?
The wavelength is actually it's between 400 and 700 nanometers, but it's like one filter. So there's no multiple wavelengths. There's only one observation. Yeah. And so we do have some preliminary results. We have so far received 6% of the entire data set. Null hypothesis that we have no events. So basically, to get an event, you must be able to reject the null hypothesis that there is no event at a significance of 8 times 10 to the minus 9 that corresponds to having one false positive in our data so far. And we actually found a handful of events which have similar or higher significance. So that means that provided that there are no instrumental effects we haven't accounted for yet, or correlated noise, or the things we didn't take into account, that there actually might be some real events in this. And one of those I have here. So this is again time. This is a photon count. The red part with the arrow bars is the actual data. The blue line is the full template that is fitted, and the purple dots are its integrated points, which are compared with the fit. Because you need to integrate with the sample at 40 hertz, so sampling this blue template at the 40 hertz gives you those points. So this is the fit. This would, so we can get the velocity from the width of the signal. We can get the size of the object from the amplitude. And the best fit values is that it's an object of 480 meters in radius, and the relative velocity during the observation was 30 kilometers per second. So how can we check if any of this is believable, apart from the fact that it looks nice? From the observations, so now we can go and check with what we actually know from the observations. From the observations we have that the angular size dependent by the star is 0.3 on the Fresnel scale. So this part is good. If it would have been larger than the Fresnel scale, we shouldn't have seen a diffraction pattern. So this part is good. Then the ecliptic latitude is 14 degrees, which is also very encouraging because 60 to between 60 and 80% of our stars have ecliptic latitudes above 20 degrees. So there's still probability you get it by chance, but it's quite encouraging that it corresponds to lower ecliptic latitude star. And what I personally find most encouraging is the relative velocity, which we get from the observations by accounting for the motion of the cathode object, the motion of the Earth at time of the observations, and HST's velocity also comes out at 30 kilometers per second. So this is very encouraging because there's nothing we tested before or we selected before. When we search for on our data, we take the entire data set without knowing where the observation was taken or anything. We just search for this template.
So would you be able to distinguish if this was an occultation by a binary?
Yeah, we thought about it.
And what kind of fraction of binaries would you expect for these kind of size of objects? I mean, because there is sort of really some mismatch, which is, I mean, there is one point which is really very strongly above your fit and you know, still very close to the main signal. I'm
You
just
mean this one?
Yeah.
Yeah, so the chi-squared is very good for this. So I mean, you always expect there's some. Okay, to answer your question, so probably you would get two patterns in a row because it will be offset in time. If it would be convolved somehow, we would not have found it yet because so far we've only searched for the most generic template. But potentially one could try to detect it. The thing is really, because there has not really been any, I would say, generally accepted claim of any of such detection, really the first step is to detect one which can be believed by everybody, and then go out for...
Well, I mean, but still, the fraction of binaries for these small mass objects is larger.
Yeah, I mean, we
don't... would
right.
try to fit a wrong template
Right.
to the data, and you would probably not get detections at a sufficient significance, and that's why I'm saying if you try...
Yeah, I mean, you could do even something simpler, which is what most groups have done because they don't have the good sampling frequency. They just look for dips, so they just average them out. And as you can see, if you would have a binary, if you averaged out, you would still detect something. But this is, in a way, I would say where our strength lies, because we can, by averaging it out, you can see we lose a lot of the signal because there's some positive parts canceling with some of the negative parts, so the signal you're looking for is much, much weaker, and so you lose a lot in significance. And also, I mean, not only for looking for binaries, we can also look for objects in the Oort cloud in the same way, and you'll be able to distinguish because the relative velocity will be different. So we should be able to tell if an occultation was made by an object in the Kuiper belt compared to one in the Oort cloud, and due to the duration of this event, because the relative velocity will be different.
The difference is small, right?
So basically, it will be 4 kilometers. So basically,
It's bounded by the Earth, not by the...
Exactly. I mean, yeah, exactly. Most of the velocity is from the Earth and HST, but we know both of them. And basically, for the Oort cloud, this would just be 0 essentially. Which for the Kuiper belt would have an own velocity of 4 kilometers. For the Oort cloud, it would be so little that essentially it would be negligible. But the 4 kilometers, if the velocities would mismatch by 4 kilometers, we would know and would not claim as a detection for something in the Kuiper belt because the difference is large enough that it would not be a satisfying fit. yeah, as I said, so we actually have several more of those events. The reason why I showed you the one I just did is that's the only one for which we were able so far to check with the parameter of the observation. So hopefully there'll be more coming soon. Potential pitfalls which you still have to look into in more detail is that maybe there's some correlated noise you haven't been aware of yet, or some other instrumental artifacts. But I'm confident that we'll be able to address all those very well because of our large control sample, we can look in detail in the number of detections as a function of detected latitude. We have the velocity check I just already discussed. Then we can look at the number of detections as a function of the annual size of the stars. Again, if the stars have an annual size of light on Pinasca, we should never detect any diffraction patterns. We can check for correlated noise. We already did it for the event I just discussed, but you can check if there are any correlated events in the two different fine guiding sensors. If there are, then clearly it must be some instrumental effect because HST was moving or the pointing was up. And then because each of the fine guiding sensors consists of 4 photomultipliers, you can also check for the actual counts in each photomultiplier to see that a signal appears in all of them, and whether there's any correlation between slight motion of the PMTs or the FGS and the signal that is observed. So with this project, we'll be able to differentiate between the different power laws between 3, 3.5, and 4, corresponding to having had a collision, but the objects are essentially a bunch of rubble piles. Power law of 3.5 would be also some collisional evolution, but that these objects have not made material strength. And the Q of 4 would be that there was no collisional evolution. We have an excellent control sample, and we expect between none or 0.4 for power law of 3 to up to 100 events for power law of 4. So this is actually, it's really quite likely that we will detect some real events. This is really unique because most of the other surveys have had timelines that are way too short that realistically you'd expect to detect anything. We so far have received 6% of the data, and we have a few promising looking events. One has a confirmed velocities and star properties. Extrapolating from that, that would mean that the number of objects with radius larger than 250 meters would be 4 times 10 to the 8 per square degree, and that the power law index would be less than 4.2. And I said, so we could distinguish from objects in the Oort crowd, and also occultations caused by objects in the asteroid. And finally, we plan, or we will make this data for the entire data set available to the astronomical community once we've received it. Yeah. Okay, I'll finish here. I'm sorry if I overran so much.
I have 2 questions from cyberspace. Norm Murray is asking about the size distribution of planetesimals. You indicate sizes between 6 centimeters and 9 meters.
Yeah.
And he's asking, would these objects not produce a lot of dust?
From collisions?
There's a limit to how much I can get.
Yes, no, definitely you would expect dust to be created from, even just from having a collisional cascade. Yes. But the question is, well, what size of the dust? So most of the dust we can observe is a few microns. 6 centimeters, I think, is usually not what we're sensitive to. But yes, it definitely would be maybe one way of one way to see whether collisions are going on in extrasolar planetary systems has been by looking at dust. And I think there have been some suggestions that there was a recent collision or some planets colliding when there was a big outburst in infrared observations.
And the second question, oh wait, there's a follow-up. Do we see infrared excesses or millimeter excesses consistent with this?
We see some excesses, but I don't know. I think they consist with smaller sizes, so not meters to centimeters.
And the second question is, either capture or giant collision will produce inclined binaries. Will the inclination and eccentricity of highly inclined binaries evolve?
Say again? What was the beginning?
Either capture or giant collision will produce inclined binaries. And then the question is...
So both can produce inclined binaries? And then?
And then the question is, will the inclination and eccentricity of highly inclined binaries evolve?
There probably will be some inclination and eccentricity evolution. For example, even just due to dynamic friction, but the exact effect dynamic friction, for example, has on eccentricity and inclination of these binaries has not yet been calculated. It has been calculated for objects in the disk, but by the binary system, and then moving to the disk, that's one of the things I was supposed to do. I'm still supposed to do. So, yes.
Any other questions?
What sort of giant stars do you typically use for the
so you're asking in terms, so their magnitudes are between 9 and 14.
They typically have fire,
I know that the photon counts we get from them is between 100 to 10,000. So signal to noise is like 10 to 100.
So it's kind of sort of like uniformly.
Yeah, they basically, like, I mean, their real purpose is, yeah, so actually we don't know how far they are. We only know their angles of planet size. They basically, I mean, there are like 10 to 7 of them. They just chosen that they uniformly cover the whole sky, that whenever anybody proposes to observe anything with HST, that there are some of those sky stars nearby. So they're not selected on any other particular criterion other
They're all
than
stable, presumably, right?
Say again?
They're all stable, presumably. Right?
Yeah, that's right. That they're stable, there are no obvious binaries, that they're bright enough. That's like their.
If the work range is so far away, I just wonder if the work house is so far away that they don't cover the star.
That they don't, sorry?
Cover the star.
They don't cover the star?
Yeah.
I see what you mean. Yeah, exactly. So this would be, you're right. You're right. So the angles of planet size, if you go out of the Oort cloud, there'll be a larger fraction of stars. They'll be larger than the Fresnel scale. And so basically there are fewer stars that would be good for looking for these applications. Yeah, sorry, yeah. That's exactly right.
The 70 diffraction hour